Okay. So main point of this problem is that both point C and A is the fixed support. So it holds the shaft tightly. So even if you apply torque at point B, it will not rotate. So they like to know how much torque will be in the point A and point C. Okay, and also what will be the maximum stress and deformation of this shaft. So if I say only stress, that means shear stress, right? Because it's subject to torsion. So it's a region AB, BC of a stepped shaft. Stepped shaft means diameter is not the same. Is made of aluminum. That means AB made of aluminum and BC made of steel. The region AB is 45 millimeter diameter. I already discussed it. The region B has 60 millimeter outside diameter and 30 millimeter inside diameter. That means this is hollow. The end of the shaft is rigidly clamped. That means it will not rotate. Find the maximum shear stress and angle of twist on each portion of the shaft if 4,000 Newton meter clockwise torque is applied at point B. And value of G for aluminum is 28, for steel is this much Gaga cascade. So we need to figure out the stress in the shaft. Now you see the right side figure, simplified view is showing that this is the hollow tube, diameter is this much, and inside diameter is this much. Right over here you apply for. Then what will happen? And yeah, you cannot use directly this torque because what is our formula? Our shear stress formula, if I write down right over here, tau equal to T into R. R means radius of the shaft divided by J, right? So J you can figure out. R maximum will be outer radius. So R is given. J is given. But torque, you cannot use this torque because we are not sure this 4,000 torque will be carried out by both shafts. Okay, we need to figure out how much will be torque in portion AB and how much will be torque in portion BC. But total torque carried out by AB and carried out by BC, if you sum these two, will be equal to the 4,000 Newton meter. Now, this is formula for shear stress. Now we have to figure out the theta, angular deformation, and this is the formula. Tau equal to TL divided by G divided by J. Now G is the shear modulus and J is the polar moment of inertia, and length of the shaft is given L. So we need to figure out the torque in AB and in BC. Now you see it works like a beam. If you beam, you apply load over here, there will be reaction at both ends, right? Since this is the fixed support, there will be two reactions and there will be moment, right? If you have force at the fixed support with this kind of keyboard. So similarly, since there is a torque at this point, then this torque will react through point A and will react through point C. It will react through point C, and so point C we are saying this is TR, or you can say T1, and torque react through point A is TL or T. Now you will have one equation, and you can say TL plus TR equal to 4,000, right? Summation has to be same. Or you can go anyway. If you think clockwise is positive, then anti-clockwise is positive, then TL minus 4,000 plus TR will be equal to 0. Excuse me. So anyway, you can figure out this equation. So you see, we have two unknown. So we need one more equation to solve this problem. And which will be one more equation? To find the value of TL and TC. You see, point B is the common point. If point B rotate 5 degrees, what does it mean? The angular deformation of AB and BC is same. That means I can say, if I say theta B, theta AB, that means theta at point B will be equal to theta of BC, because B is the common point. Now theta will be A, theta A. This will be how much? This will be excuse me, TL, that means what TL, length of AB, divided by G of AB into J of AB. Then theta BC, similarly theta BC will be TR, LBC divided by JBC and GBC. We can say this equal to this much, okay? But then we can solve it to figure out the TL and TR. So let's see how we can solve it. Other thing, this is rotating clockwise, 4,000. So I just put two sides, opposite direction, anti-clockwise. For example, you have load for beam downward, you can say the reaction will be upward in both sides, right? Similar way I did. Even you can think this will be downward and this will be upward, but this value after you solve, this value will be coming negative. So this will be ultimately same thing. So any question about this problem? Anyone? Any question? No? Okay, then share this one. So you see right over here, in this figure, I should just make a simplified view that at point B, TB, we have 4,000 Newton meter. At TC, at point C, opposite direction of this one, TC, and this one opposite direction of this one, TA. Now, you figure out what data is given. Length of shaft AB, 1.2 meter is given already. BC, 2 meter. Torque applied at point B, 4,000 Newton meter. G28 is given right over here. G equal to this much gigapascal on right side over here. GBC 84 gigapascal. GBC just gigapascal to convert in Pascal. Diameter of the shaft AB 45, DB this much. If I copy this one, that will be here to you for it. Okay. So you see, all data is already given in the problem. DOBC. DBC actually it is hollow. So outer diameter 60, inner diameter 30 millimeter. Now we can use any notation, D1, D2, you can use. Now what they like to know, what will be the shear stress at tau AB? What will be shear stress tau BC? And angle of twist, theta AB and theta BC, how? That they like to know. Okay. But in anter torsion, we have these two formula. Tau equal to PR by J and theta equal to TL by G. This formula we have. So by using these two formula, we will figure out this value of TA, TC. Also, we'll figure out the how much torque in AB and how much torque in BC. Then we can figure out the value of theta and also shear stress. So what we did, we look in the free body, in the beam, what you did. In the beam, say you have a beam, you have a load over here, you have a load over here. And you have reaction right over here, right over here. So you say reaction is upward, reaction is upward. Say this one is 100, this one is 60. Easily you can figure out, right? You take moment over here, then you get this reaction. Then summation of force along vertical direction, then you will get this reaction force, you can figure out easily. But in torque, even if you take moment, this is not the force into distance. We apply torque. So even if you take moment over here, PA, TA should not be 0. Right? That means you have 3 value, TA, TB, and also you have TB is unknown. So by taking moment or summation of force, you cannot figure out the value of TC and value of TA. So what need to do, like in axial tension member, you did a lot of free body. So you have to draw a free body. So I will try to take the shaft AB. So this is my shaft AB. So at AB, this is A, this is B, right? And at point A, I put anti-clockwise torque TA, right over here. So how much will be torque at B? If this 100 right over here has to be 100 to make it balance, right? So this is working anti-clockwise. So this will be clockwise right over here. If I has to be by same amount. If this one is 60, then this will be 60. Okay. Now, you look in the left side. This TB, left side, is TA. It was not there. Right? On the right side, it was not there. We just put extra torque there. How we can minimize this torque? So this is my TATB. Right now I draw the BC, portion BC. I draw portion BC. There is a anti-clockwise TC torque at point C. So this one I'm keeping this way, same way. This is my TC. And at point B, there was torque 4000 Newton meter. What is this one? This one was TA. So you see that this TA, it was not main problem. Over here, no TA, but I put extra TA. So how I can minimize it? You see this TA rotating clockwise. So right over here, I can put a same TA in anti-clockwise direction. Then what will happen? If you close these two bars together, then this TA will be cancelled out because this is clockwise, this is anti-clockwise. So we will back to our previous main problem, right? Because there will be no torque at no torque, but that means there is no TA in point B. So that's what I did. You look carefully, this is TA, and this TA is not there. So I need to take it out. This is clockwise, so I put anti-clockwise TA over here. Now, we keep it like that. Okay. So you see, this is TA, both is same. What will be resultant torque at point B? If you think this is clockwise, TB positive, then this will be negative. That means at point B, your resultant torque will be 4000 minus T dot A. That will be at point. And point C remains same. So what will happen over here? This value, it's supposed to be equal to the other end of the torque. That means this will be equal to the second T dot C. This will be equal to TC. So we have a simplified beam. Instead of two torque putting over here, this one, we just put 4000 minus T. Okay. Any question? Hello?
Sir, after producing 4000 minus TA as the direction is anti-clockwise, so TC will be equal to 4000 minus TA, right, sir?
We put, yeah, because we are thinking at point B, we are thinking TB is positive. Then this will be negative because TB rotating clockwise and TA rotating anti-clockwise. So respect to point TB, TA is negative. That's how you put 4000 minus TA. But any reason, if you when you solve, say other problem, at point B, you have 100 Newton meter torque, and you have say other torque TC. Just for example, for T1, this is point B. What is say TL? Okay, this is TL. So what will be resultant torque at point B? That means at point B, if you like to show with one arrow, TL plus 100, right? Then you show the
yes, sir.
Right. The same thing I did over here. Okay, what is your ID?
Sir, 91, sir.
Your ID 91. You are section B or A today? Section A, right?
Sir, A, sir.
Section A. Yeah. Section A, 8 September. You rolled 99, right?
Sir, 91.
91. Okay. Asif, roll 58. 1558. You're here. Alamin, roll 82. Hello.
Yes, sir. Alamin roll 82, sir.
Okay. Do you understand the free body?
Yeah.
Any question? No. You understand the free body? This free body? You understand
Yes,
it?
sir. Yes,
Okay.
sir.
Okay. Good. Akib, roll 45. Got here? Akib, roll 45. Not here. Roll 23. Vishal Shah. You here?
Yes, sir.
Do you understand the problem?
Yes, sir.
Okay. Tanvir, roll 40. Tanvir, roll 40. He's not here. Okay. So go back to problem. We are saying TC will be equal to this mass because at the both end torque has to be equal and opposite. So that's why we say 4000 minus PA equal to TC. Then we use this formula theta and J. So you first figure out theta J for shaft AB. Shaft AB is solid shaft. There is no hollow. So yeah. So shaft AB, you will get DAB, that means diameter AB to the power 4, J. And BC, there are two diameters at the outside and inside diameter. I put too many subscription, but you can use D1, D2 to the power 4. So this is value of J, value of JB. Now, B is the common point. There is no slip at point B. So if shaft AB rotated by 10 degree, shaft BC also rotated by 10 degree. Any point you take, say you are taking a reference point this over here. So this point after deformation is moved right over here, say point moving right over here. So what does it mean? That if you make a line from here and line from here has to be same. Because if this one moving 10 degree, this angle has to be 10. Okay. This one I am looking, it seems like a shear strain, right? But actually how deformation, if you look in the cross section, deformation will be theta. So initially, if I think the point was over here, after deformation, applied for coming over here, then your theta will be from center point to this point, from this point to this point. So this will be your theta. Okay. So now we are saying, since this is a common point, common cross section, theta both for the both shaft is same. We said that this formula equal to this. GAGB is given. This is value of GA, aluminum. This is value of GB. And this is JAB. We just put diameter to 4. This one JBC. Now we put TA in the left side, length is 1.2, and TC equal to, you put this one, 4000 minus TA into 2. Now you see from this equation, you can easily solve this TA, right? Similarly, if found TA, then you can got the TC. So after you got the torque, now you figure out the theta. just this torque, you put it over here, and this torque, you put it over here. So you'll get the theta. So theta equal to 0.0 theta AB, 0.067. That means this is coming in radian. If you convert in degree, then coming in degree. Similarly, theta BC has to be same. If it is not coming same, then it is something wrong. This one is in degree. Now, maximum shear stress. We just need to use this formula. Tau equal to TR by J. So for shaft AB, TA into R AB divided by J. So we got this much. Similarly, you figure out for shaft BC, you will get this much. Okay. So you just use this formula. Tau equal to T into R divided by J. You get shear stress. So any question? Any question? Anyone?
Sir, one question.
No? Hello, any question by anyone? No question?
Sir, one question.
Yeah, sure.
Sir, at point B,
Yes.
4000 Newton meter torque is already working.
Yeah.
So when you take section AB, there you put TA at point B.
Yes.
Why I didn't take 4000 Newton meter torque in the opposite direction to section BC and just make it work?
Opposite
Why take
section
another-
by BC. Okay. 1 second. So what is your ID?
18.
18. 18. Okay, good question. Let me share the okay. Did you see the screen?
Yes, sir.
Okay. This 4000 is external torque. That means it is already applied external. So that one you cannot move. This is shaft AB. This is BC. B is the common point, right? So we have this is point A, and right over here, this is point, this is C, and this is point B. And this is joined together by voltage. Okay. So there is, oh, sorry, by mistake, I just did the line. So this is A. Right over here, this is point B, and this is point C, right? And right over here, we have flow coils 4000 Newton meter. So this 4000, you cannot move because this is applied at this point B. External load always should be in the same location. You can transfer it other way, that when we derive the column with eccentricity, we move the force that with extra bending moment. So this one, you need to keep it right at this point. Now, what is your question? How we can say this is both end is fixed, right? This is clockwise, so I am thinking right over here is anti-clockwise. TA is working right over here. TA is working over here. Similarly, right over here, anti-clockwise TC is working here. Now, what is your question?
The question was that when you take section AB,
Yes.
you have put TA, an additional torque at section B. Why you didn't take that 4,000 Newton meter torque in the opposite direction?
In AB, right? That's you're saying.
Yes, sir. But
Okay.
in BC, you have taken the 4,000 Newton.
Yeah, but why I'm not taking it in section A, right? AB,
Yes, sir.
that I was saying. That when your question that if I take the AB, in the left side, already it has TA. TA, left side. So your question that right over here, why I should not take this 4,000, right?
Yes,
That's
sir.
your
In
question?
anti-clockwise direction. Yes.
Yeah. So I can put, say, I can put over here 4,000 right over here. That you are saying. In that case, what will be happen? TA will be how much? TA
4,000.
4,000. That means this 4,000 load torque is entirely carried out or taken by shaft AB, right? Then what will be value of TC? 0. Because TA plus TC, if you add together, both has to be 4,000. This reaction torque will be equal to the 4,000. So you see, if I put TA equal to 4,000, then TC is 0. That means member BC, there is no torque. Okay. So you cannot put at point 4,000 in AB. Other reason, I am thinking that this load will be shared by both shaft AB and BC. It will be shared by shaft AB and also shaft BC. So each shaft will be carry load less than 4,000, but their summation will be same as TC. And other thing, you asked very good question. This is anti-floating clockwise, right? So I am putting this is anti-clockwise TA, anti-clockwise TA, and this one also anti-clockwise TC. Okay, so I start from where? From left side. If I start from left side, this is my TA. So this is anti-clockwise TA in the left side. So right over here, this is TA in this side, that means point B, it has to be equal and opposite of TA. Otherwise, it will not be balanced. So you can say this is anti-clockwise. You can say this is clockwise TA. Okay. Then what will happen? This TA is not in the middle point. Then in the BC, you already have 4,000 clockwise. This is clockwise. You make this one anti-clockwise TA. So after you solve, then right over here you will get 4,000 minus TA. And right over here you have TC. And this TC will be equal to this 4,000 minus TA. Okay, that's why you cannot put this 4,000 in the portion AB. You got the answer?
Yes, sir. Thank you, sir.
Okay, but your conception we can clear more that if you like to start with the right side, say at point B we have 4,000 torque. Right over here we assume anti-clockwise. Right over here anti-clockwise TC, right? TC, this one TA, and this one 4,000. Okay. Now, your way you ask question, it is possible. We can put 4,000 with portion AB. How? So this is my point A, this is B, this is C. If I try to balance from the right side, you take first draw the free body of BC. How? I am making mistake. My mouse is giving trouble. Anyway, 1 second. At the middle, I have it is this is 4,000, and right over here, anti-clockwise TA, and right over here, anti-clockwise TC, and this is 4,000. This is point B, this is C, this is A. Okay, where I draw, I start from the left side. You start from the right side. So right side you start. This is C, this is point B. So there will be TC at point C, no doubt about it. Right? Now, how much torque we put in the point B? If you put 4,000, you can balance it. Right? Then TB will be 0. So right over here, this is anti-clockwise. So I'll put clockwise TC right over here. Then at point B equal to TC, point C also TC. Both is same, is equal and opposite. That means balance. Now we come to the TA. So TA left side is working. This is TA. This is point A. And point B, I have this 4,000 clockwise, right? This is 4,000. So now this is not balanced, because if you close this TC in the middle, there is no TC. You need to take it out. So this is rotating which direction? Clockwise, right? So over here, this will be anti-clockwise TC. Now, if you make summation of these two, then it will be 4,000 minus TC at point. That means at point AB, there will be TA, and here will be this direction, 4,000 minus TC, and this will be TA. So in that case, we'll say TA equal to 4,000 minus TC. Okay, now more clear?
Yes, sir.
Okay, good. Now, I was supposed to be TC one more problem in the core, but right now I'm just giving you some hints that how we can solve it. Sometimes I put in the exam, okay? But if we got time, then we'll solve it in detail. Just giving you, for example, you have a shaft right over here. You have a one more shaft right over here. You have a one more shaft right over here. And this shaft, you have a torque right over here. I'm saying clockwise 200 Newton meters. Right over here, anti-clockwise, say 400. Right over here, this direction 500. Okay. So if I say this is A, this is B, this is C, this is D. How much torque you need to apply at point D to make a balance? How you can figure out? You see, summation of all torque has to be 0. for balancing. You see, if you think clockwise is positive, this 200 positive, then this 4000 will be negative. Again, this 5000 will be positive. How much are you getting over here? 7 minus 400, but 300 unbalanced, right? So I'm saying this is TB. TB, not TB, TD equal to 0. So if you solve it, then you get TD. TD equal to, you'll get minus 300, right? So that means at T, you have anticlockwise 300. But you need to figure out, okay? Now, you see balance, you sum all anticlockwise. This is anticlockwise, this is anticlockwise, so 700. And clockwise 2, this 200, this 500, 7. That means balance. Now, if I say figure out the torque in each section, then how we can do it? If I say figure out the shear stress in each section, then how we can figure out? So we found right over here clockwise 400, right? And right over here anti-clockwise 200. Right over here anti-clockwise say 500. So clockwise, this is clockwise, anti-clockwise 700, right? So right over here, I need to put clockwise 300. So this is balance, right? Now, if I say, what will be the shear stress of shaft AB, BC, and CD? I will figure out. You cannot say that shaft AB has 400 or 500. No. You need to draw the three-body diagram. How we can draw it? So at first, let's I draw shaft AB, straight line. So at point A, I have clockwise 400. What will be at this point, point B? Anyone? Could be opposite of this one. This is clockwise. So at point B, there will be anti-clockwise 400. Okay. Now, how are we going to balance BC? BC, you need to balance. How are we going to balance? Now we take BC. At BC, you have clockwise 500. This is B, this is C. So this is 500 clockwise. And this B, which direction is this B? Anti-clockwise, right? So this one will be also clockwise over here. This will be also clockwise. Then it is come. How much total coming in the this side? Total. This 500 clockwise, 400 clockwise. That means 900, right? So this 900 has to be anti-clockwise. Then you can say the torque BC equal to 900. Torque AB equal to 400. Then you figure out the shear stress. So similarly, you have to put portion DC. Portion DC, I think it seems like I did somewhere mistake. It's not matching. This 400 clockwise, this 400 clockwise. So 700, right? 700. And this 500, it has to be, let me delete only this one. This is not balanced. because this is clockwise, this is clockwise, 700. So anti-clockwise has to be 500. This is anti-clockwise. So right over here, this anti-clockwise 500. Anti-clockwise mean opposite direction, right? So I put this direction. So what do you see over here? 400 clockwise and this 500 anti-clockwise. So how much we put in the this side, the right
Sir,
side?
100 clockwise.
100 which direction?
Clockwise.
Clockwise, because over here 100 anti-clockwise, so I have to put 100 clockwise. Good. What is your ID? 91
Sir, 101.
101. So now we can balance the last part. So last part, I draw it just right here. Okay, let I draw it over here. This D200, you cannot change it. We are saying this is D, this is C, right? So this D200, you cannot change it. Now at point C, 300 which direction? Clockwise, right? So this 300, this is 200, we got. So this 300 applied load, you cannot change. Now this one clockwise, right? So obviously you put this on anti-clockwise 100. So 300 minus 100, 200. So it's mass. Now we can say shaft BC, CD toward 200. Shaft BC 100. Shaft AB 400. But if you initially look, you might say shaft BC is carrying more load because both torque right over here and over here. But if you draw the feasibility diagram step by step, then you easily figure out. Okay, this is one option. What is the other option? If I draw a torque diagram, so I show you that how we can draw the torque diagram. So this is, I delete over here. If you draw torque diagram, then it is easier. Like bending moment diagram. So how we can figure out? You should start with left side of the shaft. Okay, this type of one problem should be in the exam. And for example, this is the line. That means length of the shaft. And I delete this one, my point. This one, say this one is B, this is C, this is D, and this is A. I draw a torque diagram. So this is length, upward direction, I am saying torque. Which one you want positive? Clockwise or anti-clockwise? Whatever you like. Okay. Say clockwise positive. So right over here you say torque and show it the arrow. So if I look this diagram, I know that this torque is positive, clockwise positive. So how much torque at point A is not 0, right? 400 positive right over here. And until you travel from this point to coming point B, still it remains 400. So you coming over point B. So we add this line. How much torque over here? 400. Right? Like shear diagram. 400. This is positive, clockwise. When you coming over here, there is the anti-clockwise, negative 500. What does it mean? So positive 400 minus negative 400. What is the resultant? Minus 100, right? So coming over here, point B, right over here, minus 100. Then until point C will be same. Point C, so this is minus 100. We already said that clockwise positive upward, so anti-clockwise negative is in the bottom part. Now this is minus 100, and at C, what you have? Positive 200, right? At C, you can say plus 300 minus this 100. What will come? Positive 200, right? So this will go up right over here, positive 200. You go to the point D. Point D, positive 200, and this is negative, the anti-clockwise, coming 0. That means it coming right over here. Right over here is 200. So by instead of free body, if you look this plot diagram, you'll be easily know which portion is most critical. You'll know that this portion carrying torque 200, in the middle portion only 100, and first portion carrying 400. So it's giving the same result. So this diagram is called torque diagram, like shear diagram, Bending diagram, torque diagram. Okay. Any question? No? Any question from
Sir.
anyone?
Just like this uniformly distributed load that we learned previously, can torque can be also applicable in uniformly distributed way? The same torque.
No, torque would not be uniformly distributed, but it works throughout the length. You see, I take a pen, right? My figure is not clear, but you take a pen. I take a pencil or pen. See, if I rotate, you see this and try to rotate, right? So it don't matter how much the long. If it's long, still over here will be same amount of torque. What is the difference between distributed load? Okay, just 1 second. It cannot minimize. Okay, let me share a screen and I take a whiteboard. Okay, you see the whiteboard? What is the distributed load? What is its application? Say you traveling Dhaka Borishal in a boat or launch. This is floor beam of the ship. So whenever you put something at the top, it reacts through this point, right? At the support. It might have support at the middle. Obviously, they have some support at the, say, right over here, right over here. Otherwise, you have a big ship that will be breakdown. Okay. Now, if you load over here directly, say you standing, your weight 200 kg. How much load? 200 kg into 9.8 ton. That will be Newton, right? Or this load is called concentrated load, working at single point. Now, say you carrying a steel suitcase and weight about, for example, 500 kg. You putting in the floor, right? How much it will occupy? So if you keep it over here, this much space, right? So you see, so this 500, if this weight 500, it will work through at the midpoint. If I erase, it will work through mid right over here. So you say how much will be this one total force? This will be 500 into 9.81, right? This is also concentrated load, but this is not accurate. Why? This load actually uniformly distributed within this distance. Right over here, right over here. How we can say length from here to here, your suitcase length is 5 meters. 5 meters. So total 5 meter carrying 500 kg. How much will be 1 meter? 100. So this distributed load, instead of concentration, I can say 100 kg per meter or 100 Newton per meter. That will be more accurate. But if you take the only concentrated load, that will be less accurate. You understand now?
Yes, sir.
But say you have a shaft, you are applying torque over here. This torque will be all the way distributed coming to this end. Unless you fix somewhere or you apply again torque at the middle, all the torque come to the other end. But you fix it some point, then you need to figure out the reaction torque. Okay? Close it. How long our class? Until
11:20.
12:10. Right? Okay. So 12:10 or 11:20?
Sir,
Sir,
11:20.
11:20.
11:20. Okay. So you take 5-minute break until 11:20. Okay. Take 5-minute break, then you will start something else. So I pause the recording. Okay, so this chapter is finished. Okay. So do you have any question from this chapter? No. There is one thing. I will not write down. Okay. You need to write down. What is the difference between the torque and the moment? You see, torque and the moment both have the same unit, right? Moment M and the torque unit is Newton meter or feet pound, whatever the unit is mentioned. If you torque, what happens the torque? You apply torque, you try to make angular deformation of the, or try to rotate the object, torque, right? And what bending moment does? It try to deflect or bend the object. It don't rotate. You apply bending, the object would not. For example, you see my pen. I'm doing like that. What does it mean? I'm applying bending. So I applying due to applying moment. Due to the moment, it bend the object. But due to application of torque, object rotate. Okay, one difference. Other difference, due to the torque, it create your shear stress, torsional shear stress tau. But when you apply the bending moment on the object, then it create flexural stress or bending stress. Tau equal to Tc by J. I'm sorry, sigma equal to MC over I. This is the formula, right? Or My divided by I. But in the torque, you will have different scenario. The torque equal to TR divided by J. This is one difference. And what is the distribution of bending stress? Bending stress you can apply any cross section, round, circular, even an angle or C-channel, I-beam. You can apply the, or T-shape cross section. You can apply the bending moment. But the torque tau equal to TR by J is applicable where? Only on what type of cross section you can apply this torque? Anyone? No? we can apply it only on circular cross section. Okay, so those are the differences. Your bending moment, bending stress become higher at the outer fiber. Your torsional shear stress also become higher at the outer fiber. But in if we apply bending, is there there is any shear stress developed? Yes or no? Mahfuz, roll 99. You hear? Mahfuz? 99? 91. Iftikharul Islam, 91.
Yes, sir.
Are you here? Okay. So in the beam, how many stress you got in the beam? Bending stress, then what is the other one? You know? In the bending, in the beam, Kausar, 86. You are front of the computer? Kausar? No.
Yes, sir.
You're there. Okay, in the beam, how many stress we have?
Yes, sir.
How many stress in the beam? Do you know? In the beam, we have two stress. One is bending stress, other one also shear stress. In the beam, you have,
No, sir.
you don't know, okay. Tau equal to GQ divided by IP. So in beam, your shear stress become maximum at the outer, at the neutral fiber. That means what I'm saying, if you say this is neutral axis of the beam, this is the outer fiber. So your shear stress distribution in a beam become like that. That means right over here, shear stress at outer fiber is 0, but at the neutral axis become maximum. Say you have cross section like a rectangular cross section. So in the beam, shear stress right over here will be 0. But at the neutral axis will be maximum. But in the torque, shear stress due to torque, outer fiber maximum, and right over here is 0. So in the torque, your shear stress distribution become like that. That means at the center is 0. Over here, this is tau, this will be tau. Or you can say like that. You can say shear stress distribution, the shaft is like that. This is the neutral axis. Okay. So sometimes we put question 2-3 mark. What is the difference between the torque and bending moment? Okay. So this chapter is finished. Anyone has any question? No? No question?
No, sir.
No.
No, sir.
Okay. Before that, almost it's time to take a quiz or time to give you a assignment. So normally I give a assignment, one quiz, one assignment. But in your, I missed one thing. Just 1 second. One second. I try to figure out something. Did I give you the lecture note on column? Did I give you? Okay, in the column, one thing I didn't discuss. Okay, that's it is sometimes I put in the exam. If you have two columns, say both column is long column, one is circular, other one is square. square. Both column has same area. Same area mean in circular case, what will be the area? Pi into r square, right? R to the power. And the for rectangular one, if all side is A, you can say A times A or A square. So by using this relationship, you'll get a relationship between R equal to something into A, right? Or you can get this one, that A equal to something something into R equal to this. Any one equation. So what is the problem over here? I will tell you that there is a two column. One has circular cross section, other one has rectangular cross section. Both are length same, made of same material. Both have same end condition. You need to figure out which column will carry more load. Is rectangular column or circular column? You will see more older building, they use the column with circular cross section. But nowadays, most of the people use the rectangular or square cross section. There is a certain reason, because circular column is carry less load. Even you have a same area, same end condition, and same material and same length. Okay, so you can put it L1 equal to L2, A1 equal to A2. This one equal. Then both made of same material. Then we have E, right? Value of E1 equal to E2. C is same. That means C1 equal to C2. Then we use the Euler equation. From the Euler equation, we have the formula. P critical, right? P critical equal to pi square is C. You have a formula, right? In that formula, we have L by K. You figure out this value. What I'm saying, we are saying there's a two column. One is rectangular cross section, other one is square. Both have same end condition, same length. And let me know which one carry more load. So how do we do? We are saying that both are long column. So we use Euler equation. Then you figure out P critical by Euler equation. Then say sub square one, then you figure out for the round one, P critical. Then figure out the ratio. If ratio is come more than one, then one will carry more load, right? If ratio is coming one, that means both will carry same load. And while you do the ratio, then you can, if you use C1 equal to C2, E1 equal to E2, and R relation with A or A relation with R, then you get some number like 0.9 or 0.79, or might be 1.2 or 1.0. From there, you will come. Okay, this is the that one I didn't discuss. That's why I put it over here. Now, now we will start to solve. Now we'll start a new chapter. Okay, we'll start special question. Second. Share.
Yes, sir.
Hello, are you there?
Yes,
Okay.
sir.
So we will talking about the pressure vessel. So what I like to say that you are designing example to carry the LPG in the cylinder and deliver to the home, and it is due to cooking, it is burst, and at home got fire and 5 people died, right? But in Bangladesh, nothing will be happening. You have money, you pay money under the table. But what will be happening in other country, that if somebody injured or your difficulty in the product, or design failure, the company will be liable. Company will be liable mean the engineer who will design the product, he will be liable. So for that reason, you need to make sure that you design a product, it is able to carry the load. So in the pressure vessel, what kind of load? Fluid pressure. You put air, you put natural gas, or when you put the liquid, you need to pressurize, right? For example, your birthday balloon. You bought from home, then you put load by air, by your mouth, or you use other equipment, then it is gradually expand. Why expand? Because at the wall of the balloon, pressure is applying force perpendicular to the wall. Gradually it is expand. So like a boiler is also a special vessel. And you will see in Bangladesh, a lot of time you see in newspaper, the boiler explode in the rice mill or in the garments industry and people die, right? So this is very vital. Similarly, you see in the left hand side of the figure, a submarine. Actually, it's a kind of a cylinder and a pipe, bigger diameter, both enclosed, right? So it go under the sea, say 1 mile below the sea. So what is the load there in the submarine? It experiences special load, P equal to H rho G, surrounding the your submarine. If I take cross section like that, right? So all the surrounding is right over here, it experiences pressure, fluid pressure, right? And right over here will be more at the bottom because depth is more at the bottom from the top surface, right? Other thing is still they have some inside pressure. They keep about pressure 14.7 psi, atmospheric pressure, because we live in atmospheric pressure, right? So right over here pressure will be kind of. So you design a submarine, you need to make sure that it will not squeeze. You send your soldier 2 miles below the sea level, then you have to make sure they will not, the submarine will not break down. Similarly, a industry using boiler, say the boiler or pressure tank, you need to make sure it will not explode. Okay. Similarly, you see a small tank in the bottom side of the figure that used in the house, in the car, also in the restaurant for cooking. Even you see the airplane. This is also a pressure vessel, because when you travel in the plane, you see this is kind of empty plane. You see right over here is this is called frame. This is round eye shape. It comes all over round, and you see there is some other structure right over here. This one going all the way from front to tail. Okay, and this is smaller airplane. Is a bigger airplane. How they install the seat? Say they attach the floor beam, top of the floor beam, they put the seat, and the bottom place they use as a cargo room. So airplane, why I put it over here? This is also pressure vessel, because when you are flying 30,000 feet above the ground, the inside they put some pressure, and in the airplane you cannot open the door, you cannot open the window after it taking takeoff, and they close the door, is completely sealed like a balloon. Okay, there is no chance to air getting out from the airplane when it flies. So inside is pressurized. So if you have a chance to fly in the aircraft, then you will see that your ear, you're feeling bad in the air. Especially child and elder people, they travel in the airplane, sometimes child cry. Because when take the takeoff, pilot increase the pressure inside little bit. Okay, because in the at the 3,000 feet or 30,000 feet or 40,000 feet, atmospheric pressure is less. Say atmospheric pressure is 12 psi. So our body, if I consider this is our body, outside pressure 12 psi. What is our body inside pressure? 14.7 psi. Then what will happen? More pressurized. So our blood will come out through the eye and the nose. So that's what they do. They keep the airplane pressure inside little bit higher than atmospheric pressure. So they keep it about 16 or about 15 psi. So this airplane also work like a pressure vessel. If you not design correctly, the window might be pop out. Your door might be thrown down. Sometimes we see in the newspaper, sometimes this is called skin of the aircraft. This plate actually sometimes come out due to the pressure. So those are the application of pressure vessel analysis. So normally there are two types of pressure vessel. One is thin wall pressure vessel, other one is thick wall pressure vessel. Thin and thick. So thin means ultra thin, Bangla, patla. Thick means thick wall, right? Mota wall. But you'll see, like I tell you in the column, even column is very small, but that column can behave like a long column. Even a column is very long, but it behaves like a short column. Similarly, in thin wall, a column, a pressure vessel wall is very thin, but it might work like a thick wall pressure vessel. Again, a thick wall pressure vessel is bigger size, it might work like a thin wall pressure vessel. So right now, just remember that depending on the type of the wall, pressure vessel is two types, thin wall and thick wall. Then depending on the geometry, pressure vessel might be cylindrical, might be spherical, might be hydraulic cylinder, gun barrel. If we use in our country, we don't buy the gun, right? But in the third world, the Western country, they buy the gun and say you have trigger right over here. This is gun you holding with your hand, and right over here, your bullet. Okay, and you buy a gun with say $1,000, and you trigger it for hunting deer, and this barrel is explode. Who's gonna buy this gun? So how gun barrel work? Say you have a bullet right over here, the barrel right over here is the bullet. You load the bullet, behind the bullet you make an explosion, and bullet travel faster. So that means here increase the pressure. So you need to make sure that this wall is not getting cracked. For example, I heard that in Gazipur we have a machine tools factory. Normal right now, I think the Bangladesh Army now operating that one. And that time they are trying to develop cannon, but they developed it, but they fired it until burst. Okay, so I heard that one. I feel their analysis was wrong. They didn't consider correct thing to analyze, or there might be no heat treatment of the material. Okay, so any reason, this is very important to analyze the pressure vessel. Gun barrel, high pressure pipeline, aircraft, and submarine. Those are the examples. Okay. So I think our time is over. We are keeping right over here. Okay. So anyone has any question?